Hi, in this video, I want to introduce a new kind of average called the geometric mean. The word mean actually just means average. The usual average that we've always known and loved has a technical name. It's called the arithmetic mean. But it's not the only kind of average out there. There are other averages such as the geometric mean and the harmonic mean. And in this video, I'll tell you about the geometric mean. It actually has a very important real-life application. The US Congress uses the geometric mean to decide how many seats each state has in the House of Representatives. That process is called apportionment. I have a video about apportionment, so click on the link above. Think of this video as a prequel or prerequisite to the apportionment video. Let's get started. In math, we try not to use the term average because it can be ambiguous. We use the word mean instead. First, I'll give you more information about the arithmetic mean and its significance, and then I'll go into the geometric mean and its significance in real life. So first, the arithmetic mean. If you have several numbers, A, B, C, D, for example, then the arithmetic mean is, first of all, you add the numbers together and you divide by how many numbers there are. So here there are 4 numbers, you divide by 4. Pretty straightforward. The arithmetic mean has one very important property, and that it is located at the center, or more specifically, the center of gravity, center of mass, the balancing point of the numbers. Let me show you an example. Let's say that we have these numbers. If I put all of these numbers on the number line, I'll get a graph like this. I have a 1, I have a 2, I have a 3, I have a 4 and another 4, a 5, a 5, a 5, a 5, 4 of them, and a 6. So this is the graph of these points. Well, imagine that you cut out a piece of wood or metal that has this shape. Then where is the point that would balance the whole thing? Where's the point that I can balance the whole shape on? Well, if I just take 1 plus 6 divided by 2, I get 3.5, this point. And you can tell that that's not really the balancing point, because then the whole thing would probably tip over this way, right? Because this side is a lot heavier than that side. And if I put the balancing point here, it won't balance, it'll just tip over that way, right? Because this side is a lot heavier than that side. You can actually cut out a piece of wood and see where the balance point is. But I think in your life, you have tried to balance things a lot already, that you feel like it ought to be around here somewhere, where this side feels like it would balance out that side. It's not exactly half of the blocks, but because like this point is kind of farther away, so there's a good pull on it. So yeah, it feels like 4 should be the average. Well, let's try it out. 1, 2, 3, 4, 4, 5, 5, 5, 5, and 6. If I add all of these up, 3, 3, and 3 is 6, 6 and 4 is 10, so up to here I have 10. Here I have 20, and here I have another 10, so total I have 40. 40 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 equals 4. Yeah, sure enough, the arithmetic mean or the average is 4, and it is right at the balancing point. So that's one very important real-life application of the average. The average allows us to find balancing points. And it's true for larger objects also. If you have a triangle on the plane like this, where this one has some xy coordinates, this one has some other xy coordinates, and this one has some other xy coordinates. So I'm going to distinguish them by putting in some little subscripts. So x1, y1 for the first corner, x2, y2 for the second corner, and x3, y3 for the third corner. And I average out the x's, take the arithmetic mean of the x numbers. I'll call it xam for the arithmetic mean of the x's. And I do the same thing with the y values. I call it the y arithmetic mean, subscript am. Well, if you were cutting out a piece of wood or metal that looks like this, and you would try to balance it on a stick, then where on the stick should you put it so that it balances well? Well, it's probably come out to be around this number somewhere. Well, the coordinate of that point would be the arithmetic mean of the x and the arithmetic mean of the y. The arithmetic mean of many numbers, either just a set of numbers or a set of coordinates, is the balancing point. And you can generalize this to any shape. You can have really strange shape, and engineers use calculus to find the arithmetic mean of all the coordinates so that they can find the balancing point. That's the real life significance of the arithmetic mean. It is the balancing point of the data set. Another significance of the arithmetic mean is actually a lot less complicated, and that is it's the midway point. It's a halfway point. So let's take an example. Suppose I hire you to do some work for me, and I pay you, let's say, $20 an hour. And then I promise to give you a raise every month in a fixed amount. And the goal is that in a year, you earn $32. And 1 year means 12 months. What would that look like on a graph? All right, so here's a grid. The numbers are kind of small, so I'm going to write it bigger. This is 30, 35, 25. And on the x-axis is month. The y-axis is a dollar amount. Here's 0. 5 months later, 10 months later, 15 months later. So here's our grid. And you're starting at $20 an hour at month 0. And then in 12 months, I promise you that I will increase every month so that by the 12th month, by month 12, you'll be earning $32. You would be here. That sounds like it should be $1 a month, right? That works out. Okay? And since it goes up by a fixed dollar amount a month, we're looking at a straight line kind of increase. So let's put in a straight line. So there's a straight line increase. And then the question is, what is your wage halfway through? So the ending is at 12 months, X is 12, and Y is $32. And the beginning is X equals 0, 0 months, and the wage is $20. The question is, where are we? Well, halfway through, we're at month 6, right? Halfway between 0 and 12 is 6. And halfway between $20 and $32 is $26. Well, that is actually exactly halfway here and halfway there, where the X coordinate is 6 and the Y coordinate is 26. And that is the average of the two X and Y coordinates. 6 here is equal to 0 plus 12 divided by 2. And 26 here is 20 plus 32 divided by 2. So the arithmetic mean of these two endpoints is equal to the midpoint of a line. You may recall from algebra that that's how you learn the midpoint formula. You go x1 plus x2 divided by 2, y1 plus y2 divided by 2. That's the significance of the arithmetic mean. Now, let's talk about the geometric mean. Let's imagine the same situation, but slightly different. Also $20 an hour to start. Also $32 an hour in a year. But in between, instead of giving a fixed amount in raise, I'm going to give you a fixed percent raise. Well, imagine this. If I start out with this much money, let's say if I start out with $100 and I go up by 10%, then that means the following month I have 110. And that is a raise of $10 raise. Pretty straightforward, right? But now, if I go up by 10% again, 10% of 110 is $11. So that means I go up a little bit more. And 110 plus 11 is 121. So this 10% is actually a raise of $11. And I do another 10% on top of that, that's $12.10. Because 10% of 121 is 12.1, $12.10. So now it's $102 and $32.10. This is the principle of compounding. We're talking about compound interest now. And the whole thing grows exponentially. So it goes like this. Right, so let's go back to our graph. X-axis is month, y-axis is the dollar amount. Down here is 10. I'm starting out at 20, and I'm ending at 32. The question is still, where are we halfway through? Well, if we did the arithmetic mean, then we would think that the halfway through is at 6 months and $26, right? Because the arithmetic mean is a midpoint if the whole thing is a straight line. But the whole thing is not a straight line. It's some sort of exponential growth. Exponential growth goes something like this. So that means I start here and I go exponentially to arrive there. The real midpoint is here. At 6 months, I'm not making $26 yet. At 6 months, I'm making less than $26. The real halfway point is somewhere else. Using the arithmetic mean for an exponential growth would get you the wrong halfway point. We need a different kind of average so that we can get the correct halfway point. For exponential growth and decay as well. That is the inspiration for the geometric mean. So yeah, you may be wondering why a mathematician's coming up with weird things. You know, we already have an average called the arithmetic mean. Why are we making up other averages? And this is why. Mathematicians can make up anything they want, but people won't use it if it's not useful. So the reason why geometric mean was invented and then lasted all these hundreds of years is because people find it useful. All right, what is the geometric mean? Over here, I'm going to do the arithmetic mean, AM. If you have two numbers, then A plus B over 2. If you have three numbers, it's A plus B plus C over 3. If you have four numbers, it's A plus B plus C plus D over 4, etc. That's the arithmetic mean. The geometric mean goes like this. If you have two numbers, then what you do is you multiply them together, A times B, and then you take the square root of them. If you have three numbers, A, B, C, you multiply them, A times B times C, and you take the third root of them, the cube root of them. If you have four numbers, you multiply them, and then you take the fourth root of them. So in general, you multiply the numbers, then you take the root of them, but the degree of the root is how many numbers there are. So you take the nth root, where n is how many numbers there are. So let's take an example. Let's say that I have 1, 2, 4, 8, 16. The arithmetic mean, I'm going to add them, and I divide by 1, 2, 3, 4, 5 of them. So I add and divide by how many numbers there are. 1, 2, 3, 4, 5. 20, 30, 31. And that is equal to 6.2. The geometric mean is, I'm going to multiply them, and I take the root of degree, that is the number of items. There are 5 numbers here, so it is a fifth root. If I multiply all of this out, I get 1024, and the fifth root of 1024 is equal to 4. I have a video on how to find the nth root of a number using a typical scientific calculator. And I also have another video how to take the nth root of a number using the Windows calculator, the calculator that comes with a Windows computer. You notice that this number is smaller than that number. Let's do another example with just two numbers, 20 and 32. Then the arithmetic mean is add them, divide by 2. 52 divided by 2 is 26. For geometric mean, I multiply the two numbers together and I take the second root, and the second root is the square root. There's an invisible 2 there. It's implied. Square root of 640, which is 25.298 rounded. And this number is also smaller than that number. And in general, the arithmetic mean is always greater than or equal to geometric mean. Okay, and that is because if you go from one number to the next on a straight line, then the halfway point is up here. Whereas if you go exponential, then you got start out slow, but you know eventually you'll catch up. So in the meantime, you're going to be lower. Eventually you will catch up because you're faster. But in the meantime, you kind of diddle around. So the geometric mean will be smaller. The geometric mean is going to be smaller than the arithmetic mean. The arithmetic mean is going to be bigger than the geometric mean. And many people call this the AMGM inequality. And the significance of the geometric mean is that it is the halfway point of things that grow or decay exponentially. The other significance is used in politics. And earlier I mentioned that the US Congress uses the geometric mean to decide how many seats a state has in the US House of Representatives. Apportionment. Apportionment, you're supposed to get proportionally in deciding how many seats a state should have in the US House of Representatives. You're supposed to use a proportion, right? But as you've done a lot of calculations with proportions, a lot of time you do things proportionally and you come out with a decimal. Then once you come out with decimal, then you have to decide whether to round up or to round down. So for example, if proportionally, let's say that a certain state, let's say state A, should get 10.49 seats. It's a decimal. And you've done proportion calculations before, things come up decimal a lot of times. Well, now what? Does it get rounded up to 11 or does it get rounded down to 10? Well, the usual rounding is that if it's 10.5 and up, then it becomes 11. If it's less than 10.5, then it goes down to 10, right? That's the usual rounding. Well, why 10.5? Why not 10.6 or 10.8 or 10.2? Well, because 10.5 is the midpoint of 10 and 11. If we're talking about going straight from 10 to 11 as a straight line. So in other words, the usual rounding is because 10.5 is the arithmetic mean of 10 and 11. Well, Congress says, you know what? We're not going to do arithmetic mean. We're going to be basing it on the geometric mean. This has been the law since 1941. And it says if it's the geometric mean or more, then it goes up to 11. If it's less than the geometric mean, then it goes down to 10. That's the rule that as used in Congress. Well, what is the geometric mean of 10 and 11? Well, it's 10 times 11, and then the square root of the whole thing. So that's the square root of 110. And the square root of 110 is 10.48809, etc. So 10.49 is bigger than the geometric mean. So it goes up to 11. That's the rule currently being used in the US. And you may say, why? Why is it such a random thing? Well, there are two reasons for it. There is a math justification for it. The math justification is this. What if a state is so small? We have plenty of small states in the US. Wyoming, Hawaii. Proportionally, they get 0 point something percent only. Let's say 0.1. Well, the usual rounding rule is if it's greater than or equal to 0.5, then it gets to go up to 1. If it's less than 0.5, it goes down to 0. The 0.1 would end up here, 0 seats, and that's unconstitutional. The Constitution says every state should have at least one representative, no matter what the proportion comes out to be. So rounding down to 0 is not an option. What happens if we round according to the geometric mean? The rule is if it's greater than or equal to the geometric mean, it goes up to 1. And if it's less than geometric mean, it goes down to 0. By the way, I may have gone a little fast. I didn't say the geometric mean of what. Let's go back to this example. It's the geometric mean of the two numbers around that decimal. So in the previous example, the decimal is 10.49. The two whole numbers around it are 10 and 11. Then we take the geometric mean of 10 and 11. If the state is so small, proportionally, it comes out 0.1. Then the two whole numbers around it are 0 and 1. Then we're going to take the geometric mean of 0 and 1. Well, what is the geometric mean of 0 and 1? Well, it's the square root of 0 times 1, which is square root of 0, which is 0. Oh, good. Then 0.1 is greater than 0. And so it gets rounded up to 1, just like the Constitution requires. So mathematically, the geometric mean protects tiny little states and gives them at least one representative all the time, just as the Constitution intended. Well, that's been fun. I hope you find it fun too and informative. Any questions or comments, put it in the comments section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.